Okay, this video is related to the very last example for differential equations, and this is a problem called a murder at the Mayfair, which is posted. There's a little two-page problem description PDF in Schoology, so you can find that. And then the first day, which is the second day of OCTAVE, when we went through the predator-prey information. At the end, we're going to assign a homework problem for you to take a look at. Now, there's things that you can do here, even if you're unable to install OCTAVE. There's some hand solutions that are necessary first, and then we're going to actually use OCTAVE to graph a bunch of functions rather than solve the differential equation itself. We'll still be solving the differential equation by hand. But in this final example, we have a scenario where there's a detective that's investigating a murder, and he uses differential equations, or maybe it's a she, I can't remember, uses differential equations and Newton's law of cooling to solve a murder. It's called Murder at the Mayfair. There's a PDF in Schoology for this. So for homework, what I'd like you to do is to read through the file completely, but then just complete the parts that are labeled problem 1 and problem 2. Those things don't require OCTAVE. There's two different differential equations that are solved by hand. All right. Problem 3 involves filling out a table for solutions with different values of a constant. So don't do that yet. We're going to talk about that tomorrow after we go through your solutions for problems 1 and 2. And then we'll do a second day on problem 3. Okay. In fact, I'm assuming because this that I'm telling you now is part of the second day lesson that you've already done this at this point. So if you haven't already done this, read the Murder at the Mayfair PDF in Schoology, and then complete the things that are labeled problems 1 and 2 only by hand. All right. All right, so if you have not done that, go ahead and go and do that, and then come back and watch the rest of this video. But for those of you that have done problems 1 and 2, we're ready to do, this is essentially the third day discussion. So we're going to take a quick look at the posted solution for Murder at the Mayfair. Let me see if I can open it up here. It is, let's see, solutions, here we go. Okay, so the first one said, if we look at the problem real quick, let me open up the problem itself. You've read through it. You know that you're using Newton's law of cooling here to solve a differential equation. And you're given information like at time t equals 0, which they define as 6 a.m. We know that the core temperature of the body was 85 degrees Fahrenheit, and a half an hour later, so 30 minutes later, it's dropped 1 degree to 84. The thermometer inside the refrigerator where the body was found is at 50 degrees, so that's the medium temperature Tm, and it's a constant in this case. And then they said, suggest that you define T to be positive going backwards in time. So T is going to be the time elapsed prior to, or time before we get to 6 a.m. And you're looking for some positive time when the body started out at 98.6 degrees Fahrenheit, which is normal body temperature. That would be the time of death, when the temperature was at that point, because at that point it would have immediately started cooling once the body was no longer alive. Okay, so the first one, problem 1, was after much deep thought, diff, which is the name of the equation, it's diff E equation. Okay, really crazy. Began by assuming that Mr. Wood was murdered inside the refrigerator. What's the estimated time of death? So it's just a single differential equation here for the entire time. And so the solution would be the standard solution for a differential equation of this form, which is T equals the medium temperature plus CE to the KT. And then we know that T equals 0 at 6 a.m. Positive time is backwards. That means that we have two initial conditions. We know that T at 0, time is 0, is 85, and T at negative 0.5, because it's in the future, is 84. So we could use the first value here, T, time is 0, temperature is 85, to plug in 85 here, and 0 for the time, to solve for the constant C and find that it's 35. Then plug that into the equation. And then we can use the second data point that we were given, that when time is negative 0.5, the temperature is 84, plug those things in and solve for the constant K, which would be negative 2 natural log of 34 over 35, so it ends up being 0.057975. And when we fill that in, we have a complete model that shows the temperature of the body versus the time being hours prior to 6 a.m. And then if we assume the time at the temperature of death was 98.6, you can plug that in for the time, for the temperature, and then carefully solve with pre-calculus here to get the time, and you'll find the time is 5.66 hours. So if you go 5.66 hours before 6 a.m. and then handle the decimal correctly, that turns out to be about 12:20 a.m. So that would mean time of death was 12:20 if the body stayed inside the refrigerator at the entire time. All right, and then if we keep reading, so that's problem one. Problem two said, eventually, the detective says, but what if the person was killed in the diner and then the body was moved into the fridge in an attempt to hide it? How does that affect the time of death? So then he realizes, okay, the temperature in the diner was 70 degrees, so there was an abrupt change in temperature of the body. Right? If it was killed in the 70-degree temperature, it started cooling, and then at some point it switched to being cooling at now that the medium temperature is different. And that means that the medium temperature, we could still use a single differential equation, but now our medium temperature is not a constant. So we have to have some function. And in the problem, it suggests that what you could do is say that the medium's temperature as a function of time is it starts at 50. Well, you take 50 because it starts in the freezer, because remember time is 0 is in the freezer, and then if you go back at a certain point h in time, then we're going to add 20 to that to bring the temperature to 70, but there'll be a unit step function to only make sure that that plus 20 applies after a certain time. In other words, a certain point prior to this. So to kind of see what's going on in my solution, I made a little timeline like this and said, okay, here is t equals 0 when the temperature was 85. That's 6 a.m. We know at 6:30 a.m., a half hour later, so t is negative 0.5. The temperature has dropped to 85. Right? The time of death is somewhere back here, but now we're postulating that the person was killed in the diner at 70, and then at a time t plus h, so h hours before, that's when this changes to 50, and that's where this comes from. Right? It's going to be 50 for all the times going back from t equals 0 up to h, and then at h, it's going to switch to 70 by adding 20, only applicable with the unit step function. So if we plug this expression in here for Tm, then we can solve this differential equation. Here are the steps. Right, so this becomes Kt minus Ktm. And so when you multiply that out and bring the Kt term to the other side, it's a first order linear differential equation. But there's a crazy right-hand side that includes the unit step function. So we're going to be able to solve this, we're going to have to use the Laplace transform method. So we take the Laplace transform of everything. So the derivative becomes sys, although y is t here, so I labeled that ts, minus the initial time, or initial temperature. And then for the kt term, it's minus kts in the s domain. And then for the minus 50k, that's a constant, but the constant is times 1 over s. When you transform a constant to Laplace transform, it's multiplied by 1 over s. And then for the minus 20k unit step function, the Laplace transform of a unit step function is e to the negative hs over s. Okay, and then you can gather all the terms with the t's in them. So if I pull those together, we have s minus k times ts, and then plugging in for this initial temperature 85 at time 0. Then we can go ahead and solve this for ts. So I'm going to move the 85 to the other side, divide everything by s minus k, and so we get these three terms. Okay, these two terms are multiplied by 1 over s times s minus k. So I employed a partial fraction expansion. And because there were constants involved, I couldn't really use the online one, so I did it by hand. 1 over s times s minus k is some constant a over s plus a different constant over s minus k. And so getting a common denominator and multiplying the a by s minus k and the b by s, you end up getting that in the numerator, it's a minus b times s plus negative a k has to equal 1, and so therefore a minus b has to equal 0, and negative a k has to equal 1, and when you solve that system, you get that a is negative 1 over k, and b is positive 1 over k. And so that means that these terms here, these 1 over s s times s minus k is here and here, they split into two terms. One which is negative 1 over k times 1 over s, and then positive 1 over k times 1 over s minus k. So expanding these three terms become 5 terms because these two expand into 2, right? And then you can do some canceling here. Well, at this point, I just, let's see, what did I do here? Yeah, I just canceled the k and the 1 over k. So you end up with this. So you have a term with 1 over s minus k, a term with 1 over s, another term with 1 over s minus k, a 1 over s with an e to the negative hs, and a 1 over s minus k times e to the minus hs. Now we want to go back to the time domain by doing the inverse Laplace transform. So the left side becomes temperature as a function of time now instead of the Laplace variable s. And so this 1 over s minus k becomes e to the kt. The 1 over s is just 1. This 1 over s minus k is also e to the minus k over t. So those two things are going to combine to be just 35 e to the k over t. In this last step, those combine. But then this e to the minus hs 1 over s, this is equivalent to just the unit step function for h. So it's unit step function of t minus h times the constant 20. And then this right here, which is that e to the minus hs times 1 over s minus k. This 1 over s minus k is an exponential when we do the inverse Laplace transform, but by multiplying by e to the minus hs in the s domain, that's equivalent to a time shift of minus h in the time domain. So this is actually e to the k t minus h, but also times the unit step function t minus h. Right, so just lastly, combining this e to the kt term and this e to the kt term, we end up with 50 plus 35 e to the kt plus 20 times the unit step function t minus h minus 20 e to the k t minus h unit step function t minus h. And this k here is the same k from part 1, the 0.057975. So this is where you should have gotten to when you did the homework last night. Okay, so now that we've got that, we're going to move on. Problem 3 says, go ahead and fill out different times, well, try different values for h. In other words, assume that the body was moved at different times, numbers of hours prior to 6 a.m. So this 12 here means that the body would have been moved from the diner to the freezer 12 hours prior to 6 a.m., which would be 6 p.m. So 11 would be 7 p.m. and 10 would be 8 p.m. and so on. And so we want to evaluate what the time of death would be by figuring out, okay, if we solve this differential, well, this is the solution to the differential equation. We plug in different h's and then plot the curves. We could see at what point, at what time, graphically, is the temperature 98.6. So because that's difficult to do quickly because of the unit step function, for example, we can't plug this in easily into a TI calculator because a TI calculator doesn't have a unit step function. We're going to go ahead and use OCTAVE for this because it turns out OCTAVE does have a unit step function that you can use. So we're not going to use it to solve the differential equation. The equation's already been solved, but we're going to see one last thing that you can do with OCTAVE. We can just use it to graph equations that are hard to graph with other technology. So we're going to need a unit step function. Now, normally that is included if you have a full installation of MATLAB, and it can be included in OCTAVE, which is a free version of that, if you install certain add-on packages, but that's cumbersome to install. So what we're going to do is I'm just going to write, we're going to include a file, which is a unit step function. Now in OCTAVE, that step function is typically called the Heaviside function, named after Oliver Heaviside, who's a great in mathematics. Actually, a lot of the things in Maxwell's equations that are attributed to Maxwell, some people consider Heaviside to be at least partially responsible for that. For sometimes people call those the Maxwell Heaviside equations. But anyway, so I'm not gonna explain this. It has to do with conditional statements here, but basically this function replicates the library function in OCTAVE if we could install the package to do a unit step function. So you can give it an x and you can give it an h, and it'll return the value of the unit step function. So what we're going to do is just type this exactly in as a function file. So if we go to OCTAVE now, we're going to have a file that I'm going to call heaviside.m. You can copy one of your other function files and just rename it Heaviside, and then change this to Heaviside, and then just type this exact line. Again, I'm just going to enter that directly as is. This is something we got off the internet as a way to avoid having to install the package to get this. That's usually built into the language. Okay, but we do need a function file. We're not going to, I'm sorry, we're going to need a script file, but we're not going to need a separate function file because we're not going to use the ODE 45 function to actually solve a differential equation. We solved it by hand. We're just going to use other things in Octave here. So there's another file here. I'm just calling it mayfairscript.m. You can call it anything you want. And we're going to go through all of this here. I'm just going to go through it actually in the notes where it's easier to read, and I'll explain what's going on here. So this shows you some other things that you can do in Octave. Clear all CLC, we know what that is. Tmin, -0.5, Tmax equals 10 is pretty obvious. We're going to start plotting at half a second or half an hour before to 10 hours above. But this line here, t equals tmin colon 0.1 colon tmax, specifies a range of time values along with a step size. It means consider all the times between the minimum and the maximum time, which are defined with these constants, and do that in steps of 0.1 hours. Okay, h, this is the value for the time that the body was moved in hours prior to 6 a.m. We're going to repeatedly run this with changing that to different values. And then here's our k constant. I'm just going to enter it here rather than having to type it into the equation. And then I'm just going to enter this equation, this temperature equation, as a function of time directly. And when I get to these unit step functions here, I'm going to enter the Heaviside function. So since that appears in two places, the first thing I'm going to do is I'm just going to, let me do this with a pencil here. So since we have that here and here, I'm just going to take what's multiplied and say it's 20 and then times 1 minus e to the k t minus h. And then that is what is multiplied by the unit step function. Okay, so that I don't have to type Heaviside function twice in here. So this is actually what's going to get entered. So here I've got, here's the 50. Okay, I've got a 35 times and a dot times because this is basically an operation on multiple time values. EXP is the way you indicate e raised to. So EXP k times t. And then we've got 20 times 1 minus e to the k times t minus h, and then dot multiplied by this Heaviside function, which multiplies by the unit step function t and h. Okay. So this gives temperature as a function of time, and the constants filled in, and this will easily allow us to run this over and over again with different h values. Okay, this line here, hold on, what this does is it makes it so that the plot doesn't clear, so that if I run this over and over again, it keeps adding the new plot to the old plot so we can see them all on the same curve, or all on the same plot. Then we're going to do a plot where the x value is temperature, the y value, the x value is time, the y value is temperature. And then we're going to add a line to go from Tmin to Tmax, and then at the y, I want it to start at y is 98.6 and end at y is 98.6. So it's a horizontal line at the temperature 98.6. Line style, make it dashed and the color red. So this is just adding a dotted line at the temperature 98.6 so I can easily see when our curve intersects that so we can determine the time. And then this is giving me a range for axis. I want the horizontal axis to go from Tmin to Tmax, and the vertical axis to go from 80 to 100. All right, so if you enter that in your script function and then you execute, you'll get, let's see, yeah, you'll get this right here. So here's the dotted line at 98.6. Here's the temperature as a function of time. And what this means is, remember, we're going back in time. So this is the body rewarming up as we go back to the time of death. And this is the time of death. The time of death is when the temperature of the body was 98.6. This is telling me from using my kind of cursor down here that when h is 2, it looks like the time of death, well, the time of death would have been 8.7 hours prior to 6 a.m. So the t value is 8.7. right? And we could enter that in a table. So they gave us a little table for this. So we could, well, let me do these other curves. So if we then try these other values like h is 3 and save and run, what should happen is it should just enter another curve. So this was h is 2, this yellow curve is h is 3. And if you do h is 4 and you keep running this over and over again without clearing, the hold is on there, then it keeps adding curves. So what's happening is the time of death is changing here, right? And if you do this through all the values that they suggest in the table up to 12, you end up getting this right here. So h is 2 is this one, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, and 12 all are just this line. So there's no perceivable difference, okay? And so what you could do then is for every one of these h values, you can indicate the time t that the time of death was prior to 6 a.m. All right, so at this point, I've published in Schoology those curves. So you can go find a Octave output plot if you don't have Octave installed. If you have Octave installed, you can use the information in this video here or the notes to go ahead and enter this yourself in Octave. But for everybody, I'd like for you to use these t values and then go ahead and fill in the rest of the table. Fill out what the time of death was, fill out what the time the body was moved is, and then go ahead and answer problem number 4, which describes 3 suspects, Twinkles, Slim, and Shorty, and asks which person is the detective going to investigate. The information in this table will help you to solve that. All right, so that is that's the end of the third day. Now, rather than make another video, I'm just going to go ahead and on this video describe the final solution. But you should do this yourself. Go ahead and try to solve this and read through and figure out which of these 3 suspects is most likely to have committed the murder if the body was moved. And then come back and watch the last 5 minutes of this video. So assuming that you've tried it, here's what I got when I solved it. So if you plug in 5.7, that means 5.7 before hours before 6 a.m. means that all these numbers here are 12:18 a.m. 6.2 would be 11:30. 7 would be 11. 7.8 would be 12:10, and 8.8 would be 9:12. And then there's a bunch of commentary in here about these different subjects. Like it says that the first is Mrs. Wood's ex-wife, a dancer by the name of Twinkle. She was seen in the Mayfair between 5 and 6, engaged in a shouting match, and then she left at 6 p.m. So Twinkles was arguing between 5 and 6 with the victim, and then left at 6. There's a second suspect, an East End bookie, who goes by the name of Slim. It was in last night asking for Joe around 10. Witnesses says there was a lot of hand gesturing, like Slim was upset about something. So they were also arguing around 10. And then witnesses, Slim stormed into the back room and he left quietly out around 11 p.m. Okay, so he was in the restaurant till 11 p.m. and there was arguing going on until 10 p.m. The third suspect is the cook, whose name is Shorty. It says they were arguing also. And then Shorty took an unusually long break at 10:30 p.m., took off in a huff when the diner closed at 2 a.m. Okay. And then he says, great work, partner. I think I know who to bring in for questioning. Who does DiffyQ want to question and why? All right. So the first thing, if you look at this, is some of these times of death are not really going to be possible. All of these ones here where t was 5.7, that's not possible because the time of death would have been after the body was moved, right? The body is not going to be moved until after it's been murdered. So all of these are not possible. And then I took this 4 a.m. one off with time of death at 9:12, also because people were arguing up until 10 p.m. with the victim. So he can't have died before 10 p.m. So that leaves these 3. The time of death could have been 10, 12, body moved at 3, or 11, body moved at 2, or 11:30, body moved at 1. And since you can't, since these are only three that are left, if you look at when people left, there's only one person that was in the restaurant when the body could have been moved at either 1, 2, or 3, and that's Shorty. So all the other suspects had left the restaurant by 1 a.m. So Shorty would be the one that the detective would be calling in for questioning to discuss this scenario. All right, so kind of an interesting problem that shows how you could use differential equations to solve a forensics problem. Kind of interesting. All right, that is the very last topic for differential equations. You've completed the course at this point, except for taking the final. So we'll talk next week about how we're going to prepare for the final exam.